Okay, this is using Q, which basically is exactly the same setup as equilibrium constant K, same sort of fraction, but it's when their system, when you're not sure if it's at equilibrium or not. So if it's at equilibrium, then Q and K are exactly the same thing. So they're both this fraction where the concentration of products on reactants to the mole ratio number. Remember, the square brackets means concentration. So if Q is greater than K, so if you've got some concentrations of your products and reactants, you put them in your expression and you get a number and it's greater than the K value, then you know it's not at equilibrium. But it also means for a fraction to be higher than another fraction, the number on the top must be larger, which means that you have more products. So if you've got too much products, you're not at equilibrium and you've got too much products, then you're going to have a back reaction, so that an overall back reaction, and the way of saying overall is net. By overall it means that there's still a forward reaction as well as a back reaction, but there's actually more back reaction. So an overall. This is because the actual rate of the back reaction is faster. So once you make enough reactants, then this number goes down, that number comes up, and your Q value will become smaller. So the opposite, if Q is less than K, so if this fraction is less than that fraction, smaller number, for a fraction to be smaller, the number on the bottom has to be larger, which means there's too many reactants, which means that some of the reactants will be turning into products to make the reaction, the fraction larger. So there's more reactants compared to products, so the system will have a faster net forwards rate. In other words, the system will shift in the forwards direction until you reach equilibrium. Okay, we'll do an example. The equilibrium constant for this reaction is 4.5 at 80 degrees. So they've got this mixture of moles in a 2-litre vessel at 80 degrees, and you have to decide if the reaction is at equilibrium. And if it's not, which direction should it shift? Should there be more forward or back in order for it to get to equilibrium? Alright, so the reaction quotient is the products on reactants, and we're calling it Q rather than K because we're not sure if it's at equilibrium or not. So we have to work out, you can't use moles directly, you have to turn them into concentration. Always be really careful that you can't use moles. So once you've got your concentrations, then you can plug them into your equilibrium expression and see if it's the same number. So in order to be at equilibrium you need 4.5, you've got 0.23, so clearly it's not at equilibrium. Reaction quotient Q is actually less, 0.23 is less than 4.5. So if the reaction is less, then it means the number on the bottom is larger. You've got more reactants than products. So for the number to get higher, you want to make more products. You want this number on the top to get higher. So there has to be net forward reaction. So you have to use up some of the reactants to make some products, and then your value will get to 4.5. So there is a shift in the forwards direction, or the rate of the forwards direction is actually faster.